ready to go?
Yeah,
Oh,
anytime.
very good. So we'll continue with Ling Lin, decision trees, Brill, Noether theory, vector light spectra, and F theory.
All right, thank you, Mike. And let me also thank the organizers as well for putting this workshop together during this time and giving me and the others the opportunity to present up some of the work we are doing right now. So this work I'm presenting right now is still in progress, and it's done in collaboration with Martin Bies, who is a postdoc at Oxford, with Miriam and Ron, and Miriam's student Muyang Liu at Penn, and with Fabian. And the motivation for this work is a very classical problem of string pheno. Namely, we want to find realizations of the standard model within the string landscape. So in particular, what that amounts to is also to have within the massless spectrum vector-like pairs that can accommodate the Higgs. More generally, if you think about just understanding quantum field theory from string compactifications, the vector-like spectrum is part of the characterizing features of a 4D vacuum. So if you want to understand, for example, the field theoretic moduli space of some 4D supersymmetric vacua, or how certain theories behave under RG flow, then having a good understanding of how the vector-like spectrum depends on the geometric parameters is vital. In F theory, this is not so straightforward given the non-topological nature of the vector-like spectrum, which is to say that the number of vector-like pairs depend in a very intricate way on the complex structure parameters. And in order to tackle all these problems I've just mentioned, we need to establish firmly a good understanding of this precise relationship. And given recent development and also showcased in the previous talks, one question that we had is how can machine learning techniques or data science techniques help with addressing these problems? So for the talk to make sense, I'll have to explain how to compute the vector-like spectrum and F theory models in terms of line bundle cohomology, and hopefully convince you that this is a difficult problem in practice. Then I'll discuss the machine learning tools in terms of a decision tree that we apply to tackle, hopefully to solve some of the issues. What we find is that we actually gain some pretty practical, intuitive understanding that we can sort of apply directly to a toy model without much deeper geometric understanding, and see that we can indeed engineer some additional vector-like pairs in the toy F theory model. But in order to have a full understanding of the moduli space of these cohomology jumps, we really need to combine these kind of insights from machine learning also with some more sophisticated mathematical tools, in this case, Brill Noether theory. Okay, so for the purpose of my talk, I'll just think of F theory as a type 2B compactification with 7 branes on a Kähler threefold, where the back reactions of the 7 branes onto the string coupling have been geometrized into an elliptic vibration. And we're interested in the n=1 gauge sectors on these space-time filling 7 branes that are wrapped on complex surfaces in the base of the vibration. And the matter charged under these gauge sectors will be localized on curves inside these surfaces. And for the chiral spectrum, to have a chiral spectrum in these models, we need to turn on a gauge flux background. And in this case, the chiral excess is a topological quantity, and it can be computed by now very efficiently in terms of intersection theory. And the tools developed by these works have in particular led to some explicit constructions of literally quadrillions of standard model-like 3-family models in F theory. When it comes to really the number of chiral and anti-chiral modes, however, these numbers depend more sensitively on the complex structure, or I should rather say it depends on the Wilson line degrees of freedoms of the flux, which is encoded by the intermediate Jacobian of the fourfold. And this intermediate Jacobian is a rather unwieldy object in practice. And what these gentlemen here have provided us with is actually a computationally more feasible way to parameterize these degrees of freedoms in terms of Chow classes. And that just means, I mean, I'm just reducing all the fancy mathematical background to a single sentence, which just says that I can represent a flux including Wilson-Land degrees of freedom in terms of a Chow class. And from that, I can extract for each matter curve a line bundle on that curve such that the cohomologies count the left and right-handed massless modes. And as I said earlier, the chiral index is a topological invariant. So given the line bundle, the chiral index is fixed, and just knowing H0 will also determine H1. So in the following, I'll be mainly focusing on computation of H0. So in this global description, the line bundles are given in terms of points as a collection of points on the base. I will come back to the, and this description just is specified by the global data specifying the vibration in terms of some polynomial equations, essentially. And the points are just some common vanishing loci of some polynomials. And such an object can be modeled as a coherent sheaf on the base. And there are by now certain tools in terms of X groups and where you can compute these cohomologies of line bundles algorithmically. And this has been implemented in a computer algebra system by Martin in his doctoral thesis called CAP. And while this description in terms of sheaves and also these algorithms are very general, meaning that, for example, they don't require the curve to be smooth, they are computationally very resource intensive. And so, for example, they fail to produce a result on a computer if the genus of the curve becomes too large. However, in typical F-theory models, global models, there are curves where the genus oftentimes exceeds these bounds. And actually, funny enough, these precisely correspond to the curves that would be hosting the Higgs in a phenomenological interpretation. Moreover, because these global models have order of hundreds of complex structures or even more, really determining an explicit the dependence of the vector-like spectrum on the complex structure is very tricky. And in addition, these kind of sheafy description lack sometimes a local type 2b-ish intuition about the matter, and this can be somewhat hindering if you want to compute, say, Yukawa couplings in global models. So the first order question that we want to answer in order to eventually resolve these problems is, what, given any global model, can we say what the generic value of H0 is? And under what circumstances does that jump? Meaning, when do I get additional vector-like pairs? And so we resorted to a machine learning approach to try to tackle this question. And recently there has already been some interesting studies of using machine learning to learn line bundle cohomologies. I should say that these works are mostly suited for heterotic compactifications more than F-theory in the following sense. Namely, the space on which I want to compute the cohomologies are usually smooth and are inherently given in such a way that the Picard group, so the set of possible line bundles, is known. And also the data specifying the line bundle is basically in the most natural way that there is. Let me contrast that to F-theory. In there, the global models usually just specify, as I already alluded to you, the curves and the line bundles just in terms of some polynomials on the base that are related to the data specifying the full vibration. So in particular, the curve can be singular in these cases. And moreover, the Picard group of these curves are in general not known. So for example, if I specify the line bundle as a set of points on the base that happen to line the curve, then it's a non-trivial question to even answer when are certain points equivalent to each other and when they're not. And moreover, if I think about the dependence on the complex structure of the fibration, of the F-theory model, then in general, both the curve and the line bundle will be changing simultaneously as I vary the complex structure parameters. So, of course, in principle, the algorithms that are implemented in the computer program should be able to compute compute the vector-like pairs in these problems, in these cases, but because it's so inefficient to use them in concrete models, having a machine learning on real data seems unrealistic because, frankly, we cannot generate enough data for non-trivial cases. So instead of trying to train an algorithm that has an optimal predictive power to just say for us, given some line bundle and curve specified by polynomials, what the cohomology is, what we want to do is to train maybe on a subset of maybe less realistic examples, but learn from the way the machine predicts the jumps in a geometric fashion. And for that, we choose binary decision trees. So here's a one-slide summary of decision trees. They're basically a directed connected graph with a unique root vertex. So basically each node of the graph has arrows emanating and pointing towards them. And in the binary case, each node only has either 0 or 2 subnodes. So only 0 or 2 arrows point away from each node. Those nodes that have no subnodes are called leaves. And now in order to, so the data that I feed into the decision tree is organized by some numerical feature that I collect in a vector X. And what the decision tree does is it tries to classify an input drawn from this data by applying splitting criteria at each node. The splitting criteria are typically of this form. And if that's satisfied, then that input is assigned to one subnode, and in the other case, to the other subnode. And in the ideal case, at the leaves, so at the very end of this decision tree, one should ideally end up with all inputs of the same class for a single leaf. So for us, in the ideal case, if the trained decision tree can predict perfectly, then it would tell me exactly whether or not the cohomology jumps in that case. However, in general, that's not possible, or it won't be possible for us. And the failure of that is measured by the so-called Gini impurity, which is just a measure for how many different classes have been assigned to a leaf node. And for training purposes, what we want to do is basically minimizing this impurity. And to perform that training, we collect some data on curves ranging from genus 1 to 6 on a DP3 surface. So these cases can be easily handled with that computer program. The way the data is organized is first we take a curve class of a certain genus. That curve class has an associated polynomial whose vanishing defines a generic curve in that class. These polynomials are expressed in terms of some homogeneous coordinates of the DP3. And for each class, we then consider up to 13 different line bundles, which in this case are line bundles on the DP3, which we then pull back to the curve to define a line bundle on the curve itself. To actually get the data, what we have to do then is for each pair of curve class and line bundle, that by the way fixes the chiral index, we specify now concrete curves by specifying the values of the coefficients to be certain integers. And in our case, we just, for simplicity, choose either 0 or 1. And then we compute the cohomology of the line bundle on that particular curve using the computer program. This leads to, for low genus, only around 100 data points, but for high genus, we can go up to 260,000. And the value of H0, the lowest value of H0 we have for each pair is then considered to be the generic value, and anything above that is classified as a jump. Now, in order to train that, we actually consider different types of features on which we train the algorithm. First of all, we want to train using just the coefficients. In a second run, we train on the so-called split type, which is just some integer integer encoding the topology of the curve, whether how many components it has and how the intersection between various components look like. We also train the data set using the so-called intersection data, which is nothing else but the degrees of the line bundle restricted to each individual component of the curve. And lastly, we also combine the two topological features. And we use a training to testing ratio of 90:10 to see how our trained tree performs. So here's a tree as an example for a genus 3 curve and a degree 3 line bundle. The color coding is such that the more blue it is, the more cases of no jump has been assigned to that node, and the more orange, the more cases of jump has been assigned to that node. And you can see already from this kind of far away that there is a structure behind that tree, in that mainly no jump cases are further to the left and jump cases are further to the right. And now now I can make use of the fact that this is a virtual seminar to zoom in onto this otherwise non-legible slide to show you that why there are cases where the tree manages to find a node that classifies all instances in the find a nodes that have just one class of input. There are also others where there are different classes assigned to the same node. So within that node, I would have found both cases of jumps and no jumps. And similarly, also on the other side of where there's predominantly no jump cases, for example here, I also have a few instances that have been assigned to this leaf, which nevertheless exhibit a jump in the cohomology. Okay. So as for the average accuracy of these differently trained trees, it's so first we see that the coefficients, training on the coefficients of the curve reaches nearly perfect performance, and the deviation at low genus can be probably attributed to the fact that there has been no, the number of data points is just lower for these. And this makes sense because the coefficients basically specifies the setup complete. On the other hand, it's hard to think how knowing the relation between the coefficients for genus 3 curve, say, can be helpful to understand how a genus 20 curve behaves. So while this achieves high performance, this kind of the training on coefficients, it's not straightforward to interpret the result for our purposes. However, you see that also the topological criteria, especially if I combine intersection and split type, this green one, also reaches fairly high accuracy, around 95%. And these are basically topological data that it can also easily compile for a higher genus curve. So said differently, the fact that these topological criteria work surprisingly well seems to suggest that there is a chance that we can extrapolate these results we've collected for low genus curves also to higher genus. And in fact, if you look more carefully at the data, what you observe without any further algebraic geometry considerations is that the cohomology is more likely to jump if the curve factors off or splits into 2 where one of the components is a P1. On the other hand, the small fraction of failure of the topological criteria to fully classify whether a case instance jumps or doesn't jump signals that there are other sources to the jump of cohomology, which we'll come back later. But suffice to say that and one can ask a question whether or not this is really, in what sense they are rare. But from what we understand, it's more likely that they're being underrepresented due to the bias in our data set. Namely, we just chose the coefficients to be 0 and 1. And as we'll discuss later, this probably just means that cases of this type of jump just occur much less frequently with this type of data collection. Okay. So as I said, let me just, before we dig into the really geometric interpretation of the result or analysis of the result, we can right away apply this sort of practical intuition to a F-theory toy model. This is just some compact example that realizes an SU5 gauge theory on a DP3 with an additional U1 gauge symmetry, and this has been written down in Martin's doctoral thesis. And in the presence of this U1 flux, you can actually, of the U1 gauge symmetry, you can easily construct the U1 gauge background that induces this chiral spectrum. And we'll focus in the following on this representation here, for which the chiral index is 15. In this case, the curve has genus 24, and the defining polynomial has 44 coefficients. So if you want to do just a blind machine or a scan in terms of the coefficients, as we did for the lower genus cases, you'll be hopelessly lost, because with 44 coefficients, there's just too many cases we would have to consider in order to compile a representative data set. However, in this particular setup for this curve, it's easy to actually find complex structure deformations to the curve that splits off a P1. And when we do that, only 2 of them lead to a jump in the cohomology. And notice that these always have the condition that the degree of the line bundle restricted onto this component is less than -1. And by just combining the splitting of E1 and E2, we can get the increase in vector-like pairs compared to the generic value of 0, so H0 equals 15, to at least 2 and up to 5. So just by looking at the machine learning data and by extrapolating what you have to do for a higher genus case, you can sort of construct models with vector-like pairs ranging from 2 to 5. However, what we also observe is that in this case, you cannot get just a jump by 1, meaning in the model with a single vector-like pair cannot be obtained by just factoring out a P1. So this motivates us to look a bit more closely into the origins of these jumps. And as I just said, for the cases where the curve split, we can actually apply a counting procedure of global sections onto the various components and then correctly glue them together along their intersections. And in particular, this proceeding this way, you can easily come up with a sufficient condition for a jump to occur when one of the split components is a P1. It's just some very simple topological criteria. And this applied precisely to the examples in the toy model we have considered. One way to look at these cases is that you obtain these additional vector-like pairs because something non-generic has happened. And in these cases, it's the curve that has become non-generic. And within our data sets, this occurs often simply because these factorizations of P1s happen if you set enough coefficients of the polynomial to 0 such that the remaining monomials all have some overall power of a toric coordinate of the DP3, which happens to be a P1, or whose vanishing happens to define a P1. The cases where the decision tree fails to predict, so in other words, those cases that have been assigned wrongly to a leaf, suggest that they are actually associated to cases where the line bundle has become non-generic rather than the curve. So for example, if you consider a line bundle being a difference of 2 points, then there's a difference whether or not these 2 points are equivalent in the Picard group or not. And as we change the complex structure, such an occasion can occur without any change in the topological data defining the setup. You'll also see fairly easily that this requires, in some sense, a very precise alignment of the line bundle and the curve, which most likely is is not likely to be achieved with just setting the coefficients to either 0 or 1, and hence explains why they're underrepresented in our database. And in this case, how non-generic such a jump is actually quantified by the so-called Noether theory, where for the physicists, here the Noether refers not to Noether, but actually the father of her. So Noether theory is concerned with smooth Riemann surfaces of genus G. And in that case, I spare you the details, but suffice to say that using the Abel-Jacobi map, you can basically map line bundles of degree D on the curve onto a subset of the Jacobian of the curve, which is a smooth, which is in general some high-dimensional torus. Now you can associate to any non-negative integer a subspace inside the Jacobian, which is hit under this map by degree D line bundles that has precisely n global sections, independent global sections. In that case, Brill-Noether theory says that the dimension of this subvariety is bounded below by this number rho, which can be shown to be just this simple combination of the genus and the cohomologies. And just I remind you here again that H0 and H1 are not really independent, given that the index, the chiral index, is fixed by the degree and the genus. So in particular, this lower bound means that if rho is positive, then there are definitely certain line bundle of degree D on the curve that have H0 of a certain value n. So in the toy model that we've just considered, G is 24 and D is 38. So you see that the jump by 1, in which case H0 goes up to 16, is allowed by Brill-Noether, and it takes some time, but and some further work. But essentially, you can show that there is a suitable complex structure deformations in that model, global model, you can do so that you find precisely one additional vector-like pair. Something that, so going a little bit further, one way to interpret the statement of Brill-Noether theory and the combination with the jumps obtained by splitting of curve components is that the number of vector-like pairs induces a so-called stratification of the complex structure moduli space. That just means that I can organize my complex structure space according to certain subvarieties of different codimension, and these are lower codimension are either contained or disjoint from high codimension strata. And the Brill-Noether theory describes these stratas where the curve remains smooth, and that provides an upper bound on the number of vector-like pairs you can achieve given that the curve remains smooth. This has been shown, discussed in a paper by Taizan in 2016. However, this bound can be violated by splitting off components of the curve, or the curve becoming singular. And in fact, in global models, the perspective one really should have is that changing complex structure really affects both the line bundles and the curve topology the same way. So it makes sense to look at the strata in the moduli space that are of both types, namely with generic curve but non-generic line bundle, and with non-generic curve but generic line bundle. And for a given pair of curve class and a line bundle, one can summarize the situation actually in a Hasse type diagram. So here I have an example of a genus 5 and degree 4 line bundle whose chiral index vanishes. So the generic case corresponds to a curve that has no vector-like pair, then on the moduli space, you find that you can go up to 2 vector-like pairs while the curve remains smooth. Above that, you necessarily need to make the curve singular by splitting off some components. And you see here that the further jump can also appear by the line bundle becoming non-generic on one of the components, but not the other. But the higher you go, the more you have to resort to these kind of splitting scenarios. And the fact that this kind of diagram has this directed arrow is intimately related to the fact that the moduli space is stratified through the vector-like pair, and coincidentally also connected nicely to a diagram being a Hasse diagram. So let me just quickly summarize since I'm out of time. I hope that I have convinced you that the explicit computation of the vector-like spectrum in global F-theory models is very difficult, and the machine learning techniques that we applied can at least gain some intuition about cases where the algorithm fails to produce a result. I want to stress again that the methods we apply, the study that we're doing here is qualitatively different from previous machine learning studies of line bundle cohomologies, because in this case, we really change line bundle and curve topology simultaneously, as is the case in global F-theory models. And both changing line bundle and topology source jumps in the, and line bundle and curve topology, both changes source jumps in the cohomology that can be captured in a Hasse type diagram. And this reflects the fact that the vector-like spectra induces a stratification on your complex structure parameter. And if you want to hear more about these, the more technical aspects of this work, I also refer you to Martin's talk next week, Tuesday, in the summer series of Stringfino that Cody has set up. So let me just give a brief outlook on what needs to be done. On the technical level, there are some, we obviously need to extend it to bundles that are not pulled back. These are harder to describe, but in principle, the computer algorithm can compute. And so we just need to come up with a clever way how one can perhaps apply machine learning in these cases. But also, it would be interesting to combine the stratification diagrams that I have drawn on the last slide for a model that has several curves. So the interplay of tuning complex vector-like pairs on different curves, how that affects the stratification structure of the moduli space. More conceptually, there are some open questions, in particular revolving about how I actually incorporate in this discussion gauge backgrounds that come from non-vertical fluxes. And once we understand all these problems, it might be actually interesting to apply them to model building, but also more formal aspects of SCFTs and perhaps even the swampland program. Before I thank you for your attention, I should mention that I forgot John Stout when I mentioned that the seminar series on Stringfino. Yeah, okay, thank you.
Thank you, Ling. Very nice talk. We have time for some questions. Jim?
I guess technically Yunnan was first, but I don't know that it really matters.
Yes.
Yeah, Ling, very nice talk.
Thanks.
So what's that? Okay, I'll go ahead and ask my question. It's not that long. So really nice work. This is a great physical problem. This is a great application of machine learning. Definitely the idea of trading off and not using the neural network and maybe sacrificing a little optimization in order to get more interpretability is a good one. My understanding is that the decision tree is doing very well in the case that the curve has a P1 component. But then when it's the union of some curves that are none of them are genus zero curves, that's where it gets hard. So I guess in both machine learning and in human learning, it's interesting to study the failure modes, which is what you guys did. But my question is, this extra important bit in the case that it's a union of curves that are not genus zero, you bring in this nice Brill Noether theory. The information that you fed the decision tree initially, did it have the complete information necessary to like answer the Brill-Noether question, or was it that the decision tree couldn't have possibly done well enough because it just wasn't given enough information?
So this is a very good question, Jim. I have to confess, I don't know a definitive answer. What I said, I tried to highlight in the talk is that I think there is a bias in our database to start with that basically has only few cases of Brill-Noether type of jumps. And that basically comes from the fact that you need this kind of very acute alignment of some points on the curve to achieve such a jump. So having said that, I'm not sure that if we had enough examples in a data set that the machine learning could actually learn these type of jumps. I think it is possible given, at least based on training using the coefficient data, because there you can actually achieve almost 100% accuracy. So there, while you lose this kind of geometric intuition for what's happening, yeah, while you lose the geometric interpretation, I think nevertheless, machine is doing something in the background that is also taking into account these kind of Brill-Noether jumps.
We can't hear you, Jim. You're muted.
Sorry, I have been having connection issues all through COVID, so I need to finally fix it. So you know what, Ling, maybe I'll let other people ask questions because I missed about 30 seconds of your response,
okay, yeah,
I think.
yeah.
So I'll ask you this offline.
Yes,
very nice talk.
Thank you. Thank you.
Thanks, Yanan.
Hi, Ling. So I wonder about the structure of a decision tree. Basically, in the tree, you have many different leaves, right?
Yes.
And every leaf could be interpreted as a mini theorem. Then I wonder, like, have you checked, like, try to prove any of this particular leaf, like whether these conditions are actually mathematically correct or not?
Right. So as I said, one of these criterions that I wrote down, let me just, if I have a few more seconds to share the slide again, I shouldn't have stopped the sharing. I've written down here, do you see this?
Yeah, these are conditions inequality.
Yeah, exactly. So there's some numerical condition. And at least, I should say, at least in this case, if nothing pathological happens for how the line bundle sits on top of the curve, then you can prove just using basic Kudara vanishing theorem that in this case, the cohomology has to jump.
Okay.
So we tried, yeah, we didn't dig deeper into this, but at least not in terms of the raw data, but there is, in the paper, there will be some discussion on how you would actually go about and look at this from a microscopic perspective and really count the numbers of sections and glue them together. And this really applies to these single leaves quite a lot. Of course, as I said, some leaves, you always have some mismatch with the data because there are these Brill-Noether type of jumps that based on the topological data, you will never able to see.
Yeah. Okay, I see. Yeah, thank you.
Okay, Sven?
Yeah, very quickly on the decision tree as well. So the structure, how stable is it? So typically when you train decision trees, the features that it spits out vary quite a bit. Like, and can you see a structure that always the same feature appears at the top of your decision tree?
I would have to refer to Fabian maybe for a comment on this because I'm not entirely sure. Fabian, are you?
Yeah, I can answer now, or we can discuss later. I don't know. So very quickly answered, we didn't train a random forest, but just a decision tree. We fixed the seeding, so we always produce the same tree, and we sort of let it split on all components, and we also set it up such that it is allowed to produce nodes with a single leaf, meaning if it could possibly find any assignment of splits that leads to perfect classification, it would have. And so for if you use the coefficients, it can, and then we get 100% because the coefficients are in one-to-one correspondence essentially with, so are enough data to distinguish whether or not you have a jump. But when we use the topological data like the split types, the curve stays smooth, but still sometimes you get a jump, sometimes you don't. So in this case, the tree cannot possibly manage to do this, no matter how you see it or how long you train it. And in these cases, indeed, there's Brill Noether theory, which explains even though it's smooth, it's still jumping. And this is just not in the data set.
Yeah, so my question was basically, right, so because you have the decision tree usually gives you some hierarchy, which feature it uses first to distinguish, to separate the data, which has more importance.
Yeah, so yeah, I can show you later. So if Ling went quickly back to the slide, you could see that the first split it does is sort of whether the split type is large or small. And the way we constructed this is that small split types, here you see it splits on whether the split type is less or larger than 5. This is the first split it does. And we start with curves that have a few components. They have a small split type. And of course, if they have few components, generically, you have enough coefficients such that the curve is generic, it's not splitting, and that's why you get all these no jumps on the left and all the jumps on the right. So this is your feature selection, which it does initially.
Yeah, thank you.
More questions?
So, Ling, when it's succeeding, I think I might have missed it because of the connection issues. When it's succeeding, is it clear that the decision variable that is helping it is something that is clear mathematically? I mean, is it recovering something that's known in its success, or is it leading to some new conjecture that you might try to prove the theorem with? Or
so as I said earlier to Inan, we didn't think about the theorems too much, except for like this kind of Kodara vanishing type of argument that applies to some of the successful predictions.
yes.
But I'm not entirely sure. So yeah, this would be something that one probably has to look into in more detail.
Well, actually, that's interesting that you mentioned that. I believe Andre has a paper from last year that uses Kodara vanishing in this sort of context, but for surfaces, and they were able to prove a theorem. So it might be,
right.
But the upshot is that there's a way to understand some of the decisions in terms of Kodara vanishing.
Yeah, okay. I definitely
Thank you.
That's really
Great talk.
Thanks.
Any more questions? I don't see any. Okay, well, let's thank Ling for